right, so let's take a look at Unit 4, Lesson 12, the number E. And so we have another letter representing a constant value. It's not a variable, it's a constant value. And we've talked about some before. We have the number pi, that's a letter, and that represents, well, I should say approximately 3.14, right? We've also talked about I, which is the square root of -1. So now we have E, and we're going to take a look at what is E and how can we use it. So we're taking a look at matching situations and equations. So match each equation to a situation it represents. Be prepared to explain how you know. Not all of the equations have a match. So we have 5 equations and 4 situations, and we're going to take a look at how can we match those. So a scientist begins an experiment with 400 bacteria. So we know the initial value is 400. 400 bacteria, yeah. And all the initial values for all of our equations is 400 in a petri dish. All right, the population doubles. So doubles means we're multiplying by 2. So it's got to be one of the two, J or K. And it's doubling every 10 hours, right? So doubling every 10 hours. So that means we're looking at, if we're looking at T in hours, then N equals 10 hours. And so we want it to say 400 times 2 to the T over N. All right, so that's really going to be T over 10. And so neither of them look exactly like that, but K, that 0.1 is the same thing as 1/10. All right, so that one goes with K. Let's see, number 2, we have 400 milligrams of medicine. The amount of medicine in her bloodstream decreases by 25%. So that constant multiplier is 1 minus that 25%, to the T over N, and N is 10 hours there. And so 1 minus 0.25 is 4 times, oh, I'm sorry, not 4, it's 400. 400 times 0.75, and then we can change that to a decimal, 1.0 or 0.1 T. So that one's going to be H. Then we have the half-life of a radioactive element is 10 years. So we have 1/2, and that's going to be a 10-year increment. So that's 10 is the denominator. And then 400 was the initial value. And so that 1/2 is the same thing as 0.5. So that goes with F. And then finally, we have 400 fish, and the population is expected to grow by 25%. That seems really thick. Let's try smaller. 0.25, that seems really thin. Whatever. And then, so over the next decade, so that's T over 10. And so that is the same as G. That seemed really thick. I don't know. All right. So that is how you can match the situations with the equations that were given. Let's take a look at 12.2, notice and wonder. So a spot of mold is found on a basement wall. Its area is about 10 square centimeters. Here are 3 representations of a function that models how the mold is growing. So we have a table, we have an equation, and we have a graph. And they're all modeling the same thing. So what do you notice and what do you wonder? Well, let's see. It does look like exponential growth because you can see that this pattern is going up, and it looks like it might be a constant ratio. It's not a constant rate because it's not linear, but it does look to be exponential. And the equation kind of looks like exponential because you have this variable as your exponent. So that looks exponential. It is interesting, though, that there is an E there in the equation. That's new. We haven't had that before, although we did just talk about it in the title of the lesson. And then, well, we think that it might be exponential, so let's see if we can figure out, well, what might be that constant ratio. So let's bring up a calculator, and let's clear all that. So let's take a look at, all right, well, what is 27 divided by 10? Really, we don't need a calculator for that, but that's okay. So that's about 2.7. Well, what is 74 divided by 27? 74 divided by 27, that's about 2.74. Let's see, what is 201 divided by 74? And that's about 2.72 if we're rounding. And then 546 divided by 201. And that's also about 2.72. So if we look at these constant ratios, they're all pretty close to 2.7. Right? So the growth factor is around 2.7. So that's interesting. So it's not quite constant, but it's almost constant. All right, let's take a look at the next piece. All right, 1 plus tiny to the power of huge. All right, here are some functions, and we're going to keep that calculator out because we might need that. For each function, describe in words the outputs for very tiny positive values and very large x or values of x. So we'll do the very tiny in green, and we'll do the very large in pink. All right, so very tiny values of x for A. Really, does it matter what you plug in there? If I plug in 1, 2, 3, I'm still going to get 1, right? Oops. That was supposed to be is 1. And then the very large, if I raise 1 to the power of 1,000,000, what am I going to get? I am still going to get 1. So I'm always going to get 1 there. So my output there is also 1. So that is constant, right? Now let's take a look at B of x. If I plug in, say 1, I get -1. If I plug in 2, I get -2. And so the output is always the opposite. So if I plug in like 1/50th, I'm going to get -1/50th. And so the output is the opposite. Of the input. So for small positive values, I will get large negative values. Because remember, the smaller the absolute value of the number, when you make it negative, that's a larger number. -1 is larger than -5,000. So for large values of x, you're going to get smaller negative values. All right, for d of x, it's 1 over x. So if you plug in, say, 1/10, 1 divided by 1/10 is actually 10. And then 1 divided by 1 is 1. So the smaller x values are going to give you larger outputs, right? Is larger, right? And then for the the larger x values, your output is smaller. Yeah. Having trouble writing today. It's smaller. There we go. All right, and then when we raise f, we have f of x, and we have 1 over x to the x. Okay, that one is getting a little more challenging. And you know what? Yeah, we'll just look at that. Okay, so we have 1 divided by, I don't know, let's say 1/10 again. And then, oops. It's not, there we go. And then we're going to raise that to the power of 1/10. And so we get 1.25. And now let's see what happens if we do a larger number, we'll say 1 divided by 2. So x is 2 in this case. So then we're going to square that, and our number gets smaller. And then if we put in large values, say 1 divided by 100, and we're going to raise that to the power of 100. So as our x values get bigger, our numbers get smaller. So when we put in very small positive values, our output is larger. And then our output is smaller when we put in larger values for x. Okay, so now let's take a look at G, where we're adding 1 plus 1 over x and raising that to a power. So let's do 1 plus 1 divided by that 1/10. And then we're raising that to the power of 1/10. Struggling a little with my calculator. So there's a small value of x. It's not super small, but it's pretty small. And then we're going to we'll just do the same as we did previously. So 1 divided by 2. Oops. There we go. And then we're going to raise that to the power of 2, because x is 2, and that got bigger, whereas before it got smaller. And then here we'll do 1 plus 1/100th. We're going to raise that to the power of 100, and that got bigger, right? So this one, your output is actually smaller for the small values of x when we're looking at positive values, and then your output gets bigger or larger. I just wrote large, and that's supposed to say small. Sorry about that. All right. And then for h of x equals e to the x, we're going to use a calculator for that because we can't calculate that any other way. And again, just like with logarithms, it's a function. So you're going to tap on that function and then e, and then to the power of, and we got to go back to the main to get our numbers. And we'll just stick with 1/10, 2, and 100 again. So 1 divided by 10. And we get 1.105. Then we're going to do that again. We're going to raise that to the power of 2. Then we're going to do it one more time, e to the power of 100. And you can see that the larger input values give you larger output values. So, oops, sorry about that. So your output is smaller when you have smaller input values. And it is larger when you have larger input values. All right, and then for k of x, we are looking at 1 plus x. So we've got 1 plus 1/10. We've got 1 plus 2. And we have 1 plus, not minus, plus 100. And you can see again, your values are smaller with the smaller inputs and larger. Oh, that's really ugly, but that's okay. We'll fix that. Smaller, there we go. And when your input values are larger, your output is larger. All right, so remember that E is approximately 2.718, and we can look at that. Let's go back and see. When we put E, and E is just the same thing as E to the first, so there's your 2.718281828, and it keeps on going. What function, or what does the function G have to do with the number E? So when we looked at G, which is the 1 plus, take a look at that 1 plus. Think about, all right, well, so here we have e to the 1. So let's plug in our function for G. The G function was 1 plus 1 divided by 1 to the power of 1. And so if we look at G, it's close to 1 for small values. If we go back up here and look at our small values, it's closer to 1. It gets closer and closer to 1, and then it grows. And then for the large values, it's approaching that 2.71. Let's try putting in a really big number. So we have 1, oops. We have 1 plus 1 divided by, let's say, 1,000,000. And then we're going to raise that to the power of 1,000,000. And look how close that is to E. So it gets closer and closer to E as the output values increase. So as the input values increase. As input values increase, it approaches E. All right, what about the relationship between H and K, right? So if we look at our K values, which we had up here, what do we notice about the relationship between H and K for very small positive values? So let's take a look at that. Well, K is always 1 more than its output, right? And so very small values are going to be close to 1, and very large values are going to be very close to X. So small positive values of X for both of those two are going to be pretty close to the same. So let's take a look at that. If I do my function and let's raise to the power of, I don't know, 1/100th. And then I do 1 plus 1/100th. Those are pretty close to the same. And then as the numbers get really big, that's when they start to separate. But for very small positive values, they're fairly close to the same. Oops. All right, so that is the number E. And you can take a look at the summary if you want to read a little bit more. But we will talk in future lessons more about why do we use the value of E, why do we need that.